Hi, this is Mrs. Vrobel. This is Chapter 13, Gases. This is Part 1. So today we're going to discuss some of the properties and behaviors of gases. And you've obviously had some exposure with states of matter, but we're going to specifically focus in on gases that's trapped inside. So we're going to look at that today. So in this chapter, we're going to look at the nature of the gases, the molecular basis of their behavior. We're going to look at pressure, compressibility, diffusion. Now, I want to talk first about some constants because you'll see this over and over again with the problems. And this is something that you need to be aware of when you're working on problems. There's what we call standard state. And notice that both standard state and what we call standard temperature and pressure, they both have 1 atmosphere of pressure with the gas. However, the temperature is different. So standard state, we're looking at 298 Kelvin versus 273. And I'll tell you right now, any gas problems that you do, whenever you get temperature in Celsius, you must convert it to Kelvin. Okay, here are some units of pressure that you've seen before. 760 millimeters mercury, which is the same as 1 atm, the same as 101.3 kilopascals, or the English version, which is 14.69 psi. Okay, so the gas laws we're going to look at today are Avogadro's hypothesis, Boyle's law, and Charles' law. Now, in future videos, we'll look at Gay-Lussac and the combined gas law. And lastly, we'll look at the ideal gas law. Now, we've covered Dalton's law and Graham's law, so I'm not going to go over that in this series of videos. Okay, so what is Avogadro's hypothesis? So you've heard of his name before when we talked about the Avogadro's number. Well, he actually studied gases fairly well, and he found that equal volumes of gases at the same temperature and pressure have to have equal numbers of molecules. So that means it could be oxygen, it could be hydrogen, it could be water gas. So all of them will have equal number of molecules, long as they're at the same temperature and pressure. So here we have 3 containers, and notice that with each container we have an increase in the amount. So here we have 1 mole, here we have 2 mole, here we have 3 mole. And as you increase the amount, notice that the amount of pressure increases. And that makes sense because you have more atoms or molecules that are pressing on the sides of the container, increasing the pressure. And notice too that you also triple the volume if you triple the amount of moles of gas. Okay, now we're going to switch to another description of gas behavior, and this is Boyle's observations. And this is something that you're going to do in the lab yourself. Now, what you'll notice is with your experiment, when you multiply pressure times volume, the number that you get is the same. So it doesn't fluctuate very much. Now, you might say, well, these numbers look different. Yes, they do, but they are very close in value, so they are not necessarily not close to each other. Now, if you look at the pressure versus the volume, notice that here you have 29 inches of mercury all the way up to 117. But then you have volume of 48 inches cubed versus 12. So something is going on with this, and you're going to graph this in the lab. What happens is when we graph pressure versus volume, we actually get a diagonal that is inverse. So as you increase pressure, notice that the volume is decreased. As you decrease pressure, the volume increases. So there's what we call an inverse relationship. And this is what Boyle's law had actually observed in the lab. So he found that when you have 1 liter of gas, you have 1 atmosphere of pressure. If you reduce the volume by half, you're actually increasing pressure. If you do a quarter of the volume, notice that you're quadrupling the pressure. So the smaller the volume, the higher the pressure. And that's what I was doing with the syringe. I was actually changing the volume, and as a result, the pressure was changing. So when I increase the volume, I should decrease the pressure. Okay, so Boyle's law. Pressure is inversely proportional to the volume. So if you increase pressure, volume decreases. And I'll show you some tricks that'll help you to remember that. Please note that the temperature is measured in Kelvin. So if you are ever given Celsius, you must convert it to Kelvin by adding that number with 273. And also you need to recognize that N is in moles. So in the lab, you're going to calculate some constant when you multiply pressure times volume, and you're going to assume that temperature doesn't change and the number of moles doesn't change. We can compare this with two different gases, or two different environments. So if we say P1 times V1 equals P2 times V2, if we don't know what V2 is, we could calculate these three in such a way that we solve for the unknown volume. Okay, so here's another situation where we're looking just at volume and temperature. So we're ignoring pressure. Pressure doesn't change. But notice that when you have a small volume, you can have a low temperature. If you have a large volume, you can have a high temperature. And if you notice that each of these lines actually extrapolates back to what we call negative 273 or 0 Kelvin. So we're actually looking at absolute zero when we analyze these gases. What does this mean? Well, with Charles' law, so he noticed if you have 1 liter of gas at 0 Celsius and 1 atmosphere of pressure, if you increase the temperature, you're changing the volume by 1 over 273 of the original volume. So as you increase temperature, you're going to increase volume. So this is opposite or different from Boyle's law. We're talking about a direct proportional change. So if you increase temperature, you're going to increase volume. And as a result of this, because it's proportional, and this is sometimes confusing for students, you want to take volume divided by temperature, and that's going to give you some constant. So if we were to solve for an unknown, notice that V1 is divided by V2, and that could be equal to T1 divided by T2. So if we wanted to solve for T2, we would essentially have to take these three numbers and calculate them together.